The last talk of a session, I assume everyone is already tired. And I should say that I don't work so much in quantum info. I work more in the field of people who try to create qubits. And as you can see, I think I like sometimes to show this picture. It's from 2016, right? We have heard today more about progress on superconducting qubits, and it's really great, and you can make all these fancy experiments with error correction. But I work more in the field of spin qubits, topological qubits, Andreev qubits, and there I think we have even discussion if you have a qubit. So this is definitely not yet on the level of error correction. And that's why I thought I would today a little bit overview what we are doing on the kind of more entertaining level. So please feel also interrupt if something is not working. So one of, let's say, interesting representative in this table from 2016 are topological qubits, right? And from point of view of computation, it was a very exciting idea because we say, okay, many qubits, let's say spin qubits, they have susceptible to the local noise. So if you have spin up and spin down, let's say if you have nuclear spins or any charge disorder, we can couple to this degrees of freedom. And when we try to perform operation, we never know if we exactly grow from 0 to 1. So there's always errors, and we can hear it's not a problem. We can deal with them. But in the community was also idea that we can also design something which is topological quantum computing. And for some time, people even believe that there would be no errors because similar to, let's say, what we know that all particles could be divided to boson and fermions. And what we do, our operation would be that you never bring these particles kind of close to each other. You just move them around. And let's say we know if we exchange two fermions, we pick up the phase pi. And around this phase, there's no fluctuations, right? So you cannot have errors in this phase. And then one can go to more exotic particles, which are called anyons. There's many representative of them, but usually it's in two-dimensional system. Let's say vortices, you can also move them around, and then you have no errors. Let's say as long as you can control your path and you track what's going on in your system, there will be no errors. And this was kind of attractive idea in the beginning of the field of topological quantum computing. Why not to try to search such states in condensed matter setups? And what happened is actually not so easy to find them or to control them. And also the idea that there's no errors is at the moment, of course, under some assumptions of our theoretical model. But let me talk a little bit about this progress. As I said, the problem like with spin qubits that we confine them. And then let's say even if your confinement is changing in time because you have fluctuations on the gates, you would get errors during computations. So the idea how we can go to the topological states is to use different type of confinement, not by gates, but for example, by a superconductor, right? And the idea is simple. Instead of confining, I want to create this potential. So instead of confining it by gates, I can confine it by superconducting gap, right? And when I get states inside, now they would be not standard. They would have also superconducting pairing, and they're called Andreev bound states. So this is also now developing a state of condensed matter is to use Andreev bound state, which is a little bit combination of spin qubits, because we use a spin degree of freedom, but you have also control via, let's say, fluxes. So they also have interplay from superconducting qubit community. So this is also one of the proposals where one can consider qubits. But how actually topology occurs? So for a simple topological model, what we would need to have we have a kinetic term, right? So system moves, and then you need to open a gap, and gap we usually open by some mass term. And the idea in this simple model is that this mass could have positive sign, could have negative sign, right? And then we assumed that if you have interface between positive and negative side, then we trap a bound state here. And what is important in this model, this bound state would always sit at 0 energy, and it doesn't matter, let's say here I assume that I have a domain wall which is sharp, but I can assume that it has any profile. Just by symmetry of this problem, this state is always at 0 energy, and this is kind of first model of topology. And afterwards in condensed matter, of course, we don't have such simple spectrum, we have more complicated, we can generalize it. But the idea is here that we try to generate domain walls and pin the bound states inside this domain wall. And what is important when we call these bound states as topological, then it should be insensitive to disorder. Right, and one of a proposal which was put forward in topological quantum computing is basically bringing ingredients which we usually know from semiconductors. So we need to have a one-dimensional channel. We want to have it has strong spin-orbit interaction. And then we have a splitting between spin up and spin down. And now we need to generate this domain wall. So how we do it? So it should be two ways to open the gap. And in this problem, we have a gap. We can open it by magnetic field, because so you apply magnetic field parallel to polarization, you open the gap here, but you also can open it by superconductivity. So in our problem, we kind of lucky that indeed with two ways to open gap and compete. And if we would go to a regime when inner gap is opened by magnetic field and outer gap is opened by superconductivity, we can show that this corresponds to this simple picture of a gap inversion, and the prediction that we should have also bound states at the end of nanowire on the left and right. Right? But the question is now, like, you can say this. People, as you might probably heard, there's a lot of discussion about this platform, but if you look at the theory, there's no problem. The theory is relatively simple. But of course, when you go to the experiment, there's a lot of discussions if it could be realized or not. And the problem here goes to condensed matter, right? So what we're trying to do, we try to get semiconductor. This is material of very small Fermi energy, and we bring it in the contact with a material which has very large Fermi energy, which is a superconductor, right? Because it needs to introduce superconductivity. And for this, you need to have a lot of electrons. This is a metallic system. And the problem that you want to introduce proximity, so it means you want to have a good coupling between two systems. The stronger is your coupling, the larger is your proximity. But the price which you pay is that your spin-orbit interaction, which is absent in aluminum, also goes down as stronger you couple it to indium arsenide. So that's why you need to have really kind of a combination. From one point, you want to proximitize, but from our point, you also suppress such ingredients as spin-orbit interaction and G factor, which was initially important in order to generate these topological states. And this is what also results in discussions, what have been observed in the experiment, because of course, theory is done for very clean system. In reality, this system have a lot of disorder. It's difficult to show, for example, that they have a ballistic transports. Already 10 years ago, it was shown that we can see the system which has from disorder, and then you can see what, okay, I increase magnetic field, I get with zero bias peak. But you can see on the left, you have really numerical simulations from theories. Here we know that we have no Majorana. On the left, we have the same experiment from 2012 about some zero bias peaks with stability. And there was a lot of excitement in the beginning because it was the first time we can observe we have some bound states, right? Sits at zero energy, we apply magnetic field, it does not move, right? So in 2012, it was very exciting. We did not know what could be. So maybe it's signatures indeed of such topological states. But as time passes, we actually also considered that Andreev bound states have been studied before, but they usually studied more in the context of a metallic system where spin-orbit interaction does not play a role, because in metal, a role of spin-orbit interaction splitting is negligible comparison with Fermi energy. But if you consider semiconductors, what can actually we assume that, okay, we have nanowire, it's usually only partially covered by superconductor, because on this end, you need to attach your leads for measurements, right? So you only partially cover it. And in these states, which you can say you can have interface, right? And with nanowires, we said we have very strong spin-orbit interaction. And what we can show that due to this presence of spin-orbit interaction, even at the end of nanowire, we can get the bound states when we increase magnetic field, it goes to zero, and you can see it stays pinned here, right? And here we know that it has nothing to do with topology. It just has the effect that you have strong spin-orbit interaction, and strong spin-orbit interaction tries to renormalize the G factor, and then you lose sensitivity to magnetic field. In this case, there's no topology which is needed. You can easily get bound states with the same properties. And then you can show that, let's say, some of simulations which you do with such bound states is very similar to what you observe also in some of experiments which were interpreted as topology. And this, of course, resulted also in the community that there was a lot of discussion how to identify a knot. And then we developed the protocol, not protocol for quantum computation, but protocol how to identify it. This is work from Microsoft, because they said, okay, maybe we should not say just we have zero bias peak or not have zero bias peak. We could also look at the property that system should be gapped, or for example, that zero bias peaks should appear simultaneously on both sides, because it's one of the property of Majorana. It never comes on its own. It always comes in pairs. So if you have Majorana states on the left, you should see also Majorana state on the right. And you should check that your system is gapped, right? So that you have this gap opening and closing. And this was what put in the origin of this protocol. But it was shown that, say, with these Andreev bound states, which could appear on zero, of course, if you have a short nanowire, the same bound states which you can see on the left, you can also see on the right? Because it would also leak through nanowire if it's short enough. So if your nanowire length of around coherence length, then you can observe indeed even also the same Andreev bound states on both ends. And as well as you can mimic the appearance of gap closing and reopening due to the disorder. And this is basically says that, okay, if you have a protocol of Microsoft, you can run it, you can get false positive. So you can run simulations and you can identify, let's say, the system, because in theory we have advantage. The experiment, no one knows where the bias peaks are coming. In theory, we can run simulations, we have spectrum, but we also have wave function. We can extract wave function and check if it's run or not, or what's going on. And the problem, we can easily fail such protocol, and we can fail even in a system where have no spin-orbit interaction, because in this case, we know that system without spin-orbit interaction cannot be topological, but we can still pass. And this is a little bit the status of a field now. Let's say, is it Maran or not? There is a lot of discussion. So we're developing for protocols in this field, also trying to see, let's say, how to identify it. And let's say, as I said, this is what we are working in our group, and what is currently kind of status about topological qubits. So there's nothing to error correct. We're still trying to identify if you have qubits or not. Now, as I said, in our group, we also work with silicon quantum dots. So just give you example, let's say, what kind of problems we have with silicon or with general spin qubits, right? Well, with spin qubits, let's say we don't have discussions, do they exist or not, but we try to improve or find a good material in which we would have noise could be suppressed and you get good qubits, maybe, I mean, the record now, it's maybe we can do around 6 qubits, but the problem with realistic system is that there's no topological protection. The problem you have, let's say, about nuclear spin noise, we can get rid of if you consider some silicon isotopes which have no nuclear spins. Right, but the problem is also it has very weak spin-orbit interaction, so you also don't couple strongly via charge noise, and this kind of makes it very good spin coherence. And you can put it in the cavities, as many experiments, so everything works. The only problem, let's say, with electron in silicon is that the problem with the silicon, it has 6-fold degeneracy in the bulk, but let's say you cannot work with qubit, which has not only spin degeneracy, but also has this 6-fold degeneracy in the bulk. And this is what, let's say, what we recently proposed, because we need to find a way to lift the remaining degeneracy. So when you take bulk silicon, it has 6-fold. When we can find it in the plane, but there's still 2-fold degeneracy in 2 values are there. So it means, let's say, instead of working with 4 levels, instead of working with 4 spin qubits with 2 levels, spin up, spin down, you also have a degree of freedom as value 1 and value 2, right? And this is not good because it would result in noise, and due to the value degeneracy, you would have, because basically you can easily excite in a different value, right? And this means that you have errors which you cannot correct, and the Pauli spin blockade is not working well. So the idea is how to lift this degeneracy. And the examples how we work, for example, in theory, we have a 2-band K.P model. So we already said that we have a degeneracy which is lifted when we confine in a plane. Now we want to know how to lift also degeneracy which is left after confinement in 2 dimensions. And this is what we have proposed, especially on a 1-dimensional system, that we can actually have combination of silicon and silicon germanium. Right, so now our qubit would sit here in silicon, but we need also to find a way how to confine. And when you have 2 materials which have different composition, like here, for example, we mix not germanium to silicon, right? When in this area when 2 materials touch each other, you have strain, right? And this is a strain, is something which could help us to confine electron and the point which is the most interesting for us. And this is kind of calculations we do. We do it numerically with consoles. There's like different tensors. And what is interesting with this, in this geometry, we have shown that we can indeed generate the lifting of degeneracy by strain. And what is interesting also for us, and really kind of surprisingly useful, that our electron wave function exists exactly in this point where this degeneracy is lifted. Right? Because when you introduce shift, you also have, like now, your space is non-uniform, right? You would see that longitudinal shift would localize our wave function exactly at this angle. And also exactly at this point, we have a highest tension. So it means our wave function of electron, when we did, let's say also with applying a little bit of electric field, we can adjust it. But we can basically go to this optimal regime when your electron is exactly localized at the point where you have a maximum strain, and this is exactly the type of a strain which lifts with 2-fold degeneracy. We can show also that it doesn't have effects of disorder, or shape does not need to be perfect, but this is basically how we resolve some of the problems of valley degeneracy, which was for a long time a problem for electrons in silicon, right? So just to give you some flavor how we address. So in our group, we're also still trying to actually propose new qubits, not only work on one which exists and to improve, but also to think, can we use some magnetic system, right? Because, for example, on magnets, we know we can have ferromagnets when all spins align, or you can have antiferromagnets when you have alternation of magnetic order. And one of advantage, of course, of this, let's say if you have 1D channel, we can use also these magnons. They can easily couple to spin qubits, and also can use them in order to transmit to information, right? So let's say when you have this racetrack with this domain walls, we can have spin qubits. And this spin qubits is coupled to our domain wall. So it means that you couple, let's say, spin qubits to domain wall. You can move it when you couple to the next qubit. And this is effectively, let's say, the way how you can transmit interaction. So you can use these magnons or like magnetic degrees of freedom in order to, because for spin qubits there's also a problem how to couple them, right? So there's proposal to couple them via cavity, but we can also couple them via magnetic channel and use such magnetic channels for racetracks, right? And the advantage of magnetic systems, they also have some kind of a topological structures, right? This is like, for example, vortices. You can show that they can build up not only ferromagnetic, antiferromagnetic, but there could be much more exotic orders, vortices. And this is what we also try to use, for example, is to consider the ground states of a small, so we have can take small ferromagnetic disk, right, which in principle maybe would like to order everything is aligned. But if you have a very small disk, right, and we introduce that also we have Dzyaloshinskii-Marie interaction. And Dzyaloshinskii-Marie, similar to spin-orbit interaction, is antisymmetric and wants to make spins perpendicular, right, because it's a vector product. And then you have initial, let's say, antiferromagnetic order, which tries to make them up and down. But now if you can confine it in a small system or disk, you can end up actually with your ground state looks like this, right? So it has vorticity, right? And this is also kind of examples which you can generate. But for this, you need to have really confinement and strong Dzyaloshinskii-Marie. Right, so how it looks in theory, right? This is what we consume. We have our ferromagnet, we have effective Hamiltonian, we have here anisotropy term, Niels vector, and then we add Dzyaloshinskii-Marie circumferentially, then we can calculate it. And actually, these vortices are very funny. You can also calculate that applying now magnetic field, you can imagine that you have vorticity, which could be clockwise and anti-clockwise. And then with magnetic field, we can live with degeneracy. And these two vorticities now would serve as our kind of degrees of freedom for qubit. So it could be up and, so this line is now our new up and down, so up and low level. And by magnetic field, we can also manipulate. We can also like look at how these vortices move. It gives very nice pictures, right? And then also by antiferromagnetic links, we can also couple them to each other, right? Alternatively, I said we have these domain walls, and usually use the domain walls only to transmit interaction from one qubit to another qubit in the direction of one qubit. But you can also consider, this is new direction also in this magnetic system, to treat them not classically, but also to include quantum degrees of freedom. So now we can, usually you assume that either you spin rotate clockwise or anti-clockwise, but if this domain is small, we can also consider that actually this direction of rotation would be new pseudo-spin degree of freedom. And if this domain was composed of spins 1/2 on a small scale, we can also consider quantum effects on these domain walls. And we can similarly to consider the ways how we can manipulate with domain walls. So because now you have two vorticities. In principle, initially, let's say if you have a Hamiltonian only exchange interaction J and anisotropy KZ, when you just know that you rotate either clockwise or anti-clockwise, but these two states have the same energy. So you have a degeneracy between clockwise and anti-clockwise domain wall. But now if you apply that, we have anisotropy also in Y direction, so which is given by KY, or we also consider that we can apply magnetic field, and you can assume, let's say when I have such direction of rotation of magnetic magnetic domain wall, I can choose, let's say if I apply now magnetic field along x direction, I can make one rotational degrees of freedom or polarization more favorable than another. And this would be equivalent that I can bias these two. So I can basically split now these vorticities. They would have be two states of different degree of freedom. So this would be my Hamiltonian matrix sigma z. Another is how do I couple them? Of course, I separated here by domain wall, right? But if it's quantum object, I can consider there's also tunneling between these domain walls. So this could already lift the degeneracy between them, and this would be equivalent to matrix sigma x. What is interesting also for this, that we can control this degree of freedom also by changing magnetic field. Or what is interesting also, because we have in these domain walls usually Javorskinsky-Maria, also if we just shuffle qubit with constant speed, we can also perform rotation of a Borg sphere, because shuffling gives us also coupling of TG. And this would be additional direction for the qubits which we consider. And we can also consider, let's say, with two domain walls, when they come close to each other, you can also introduce the coupling, and this will be new proposal for magnetic system, how you can also do two qubit interactions. Right, how much time I left? Yeah, so maybe I can also talk a little bit about quantum metrology with magnons, because we know that, let's say if we want to estimate some parameter phi, then we can have initial state prepare, when we have evolution, when we measure, and then we want to estimate this parameter phi, and we want to do it with minimal possible estimation error for measurements, right? And we want to make, let's say, advantage of a quantum. But let's say if you know standard quantum limit is, let's say if you consider many spins, right? You couple to magnetic field, you want to estimate this magnetic field, which you can do by evolution, right? Because if you say you start to, you initialize your spin in some state, when you apply magnetic field, spin starts to process, and then you measure after some time where your spins are, and from this we can try to estimate what is the value of magnetic field. And of course you can assume that now you have many spins, it should work better, right? But in standard quantum limit, basically, you don't have much advantage of quantum behavior, because you know that even in standard measurement theory, your estimation error usually goes like 1 over square root of number of measurements. So now if you have spins and there are no correlations between them, you can say each spin involves in its own, and then you estimate, you still end up with 1 over square root of n. And you can say it makes sense, because it doesn't matter did you measure the spins all together, because they did not talk with each other, right? So it would be strange to get here advantage, but still the name goes as a standard quantum limit. And of course, in this case, we did not use the property of a quantum system as entanglement. And this is what was discussed in many systems. So let's say that if we introduce that now we can have entanglement or correlations between spins which go beyond classical limit, we can improve these correlations, and this dependence of m here is number of measurements, which we cannot change, but scaling with n, the n is how many states we involved, for example, how many spins could be increased, and this nu could be better than 1/2. So the ideal limit which we want to consider is the Heisenberg limit with this mu is equal to 1. Right? And this was studied, I think, in many systems, especially in optical, how to achieve it and how to use make-of with correlations is to consider that to work with squeezed vacuum states. So it means that in XP and any two variables which don't compute with each other, we don't have a circle, but we have this ellipse, right? And this squeezing parameter should help us to improve our sensitivity. And this is what we have developed, let's say, as I said, for photonic and atomic ensembles. This is a standard. But in our work, we wanted to see, can we do it basically the same with magnons, right? And magnons is this elementary excitations in magnetic system. And here we start again with ferromagnetic Hamiltonian. We have a ground state. We assume that we have anisotropy, which aligns all spins in z direction. We apply magnetic field. And then, of course, in this case, ground state, all spins are aligned. There's no magnons, and the ground state looks spherically kind of circular symmetric. Now, as I said, we work a lot with anisotropy. We can apply anisotropy in y direction. In this case, we can say that in this case, you don't know how spins align, because they have magnetic field, they have anisotropy in x direction and z direction. And then we can calculate it using Holstein-Primakov, and we can show that in this case, we got this ellipse, so we work with squeezed magnon states, and in the vacuum, we have actually finite number of magnons. Right, then we can go from a more standard procedure of calculating this number of magnons, and how experiment will be done. So we have now these magnons, and we have a spin qubit, right? And for some time, we couple spin qubits to our magnon mode by dispersive coupling. So which is basically say that with spin qubits, this sigma z produces magnetic field, which could be effectively up and down for these magnons which live in a magnet, right? And depending it's up and down, we have also different degree of squeezing. So in one case, it's some up with internal frequency of magnon, in other cases not. And this is what this achieves, even if you go, let's say we can have now ground state spin is up, and we couple to the squeeze magnon states, we have evolution, and we want to estimate the strength of a coupling. Let's say this is standard, and basically what happens when we couple, we have this squeeze qubit in the ground state, and then it evolves. And then we can show similarly to, I think, also the previous system, that indeed we can find the working regime where you are most sensitive to the phase. So this is in the case when your curvature changes the sign. And we can show that indeed, in this case, if we did all calculations, we will find that our sensitivity to the phase goes like 1 over n bar, where n bar is a number of magnons. So it means we kind of reach this Heisenberg limit of the most sensitivity which we can do. And this is again comes from the fact that we have worked with squeezed magnons, which show some entanglement. I think this brings me to the end of my talk. So as I said, I try to, we don't work so much in quantum info because the choice of the qubits which we have is spin qubits, topological qubits, and we also propose novel qubits based on magnonic system. And as you can see, I try to highlight which kind of difficulties in which field is around, and when maybe it gives us also ideas how to scale to get more qubits, and then shown when we can also run error correction schemes. So if superconducting qubits do. Okay, thank you.
So for the Majorana fermions, what do you think about this recent Microsoft thing with the Teams link and the sense charge?
I think it's a similar problem. Let's say this is what they said. Like it's kind of nice for progress which they made, but the problem, let's say, if you look at the same experiments in transport data, you do not see that you have actually gap in the system. Right, but you can see that you have some two-level fluctuation system, but it's not conclusive that it has something to do with topological properties, because this was also the outcome. But there's some two-level system which switches parity, but it was not yet shown that it has topological states. And another problem, let's say, if one would assume that you have Majoranas which are well protected and everything, right? When for Majorana fermions, initially you don't have well-defined, let's say you have for Majorana fermions, you have two ways how you can define the qubit. Let's say, because you need to define the parity, and you can say it's parity of two states in via 1 and then via 2, right? This would be one parity. Or you can define that it's Majoranas on the left ends, on the right ends, this is your two states. And this corresponds to a change of a basis from X to Z. And then from point of view, you can say, okay, this is just your labeling as an experimentalist, what you use, and then lifetime should be the same, or all properties X, Z should be the same. But experimentalists are also different by order of magnitude, which again tells you that most probably, if it's Majorana or anything topological, there's strong overlap, and you're definitely not in the regime where you want to be for topologically protected states.
Statistical verification of truth, right?
Yeah.
So and they make like bootstrapping and say this is like 65% compatible with having my edge mode, and it's like 25% compatible with something. I mean, how reasonable do you think this type of reasoning for finding good qubits?
I think, let's say, with spin qubits, you don't have this problem, right? You know, let's say for topological qubits, there's many discussions indeed about the statistical probability. So one of the problems which let's say we can estimate, when you make these two materials, you bring them close together, right? And then you have also such effect as a shift of a chemical potential. But in particular point, you need to be, in order to be in topology, you need to be close to spin orbit point, right? And your chemical potential should be inside the gap, which is opened by magnetic field. And your G factor is relatively small, renormalized, so this gap is very small. So now you can assume like, okay, if you would say, when you couple materials to each other, there's many things happening. A lot depends on interface. You can assume that you just throw your chemical potential randomly, right? And you look at the probability, how possible that you're close to this point, right? Because you cannot, then you get probability, maybe one out of 100 nanowires should work out. In other nanowires, you're basically so much away from your sweet spot that no matter how much magnetic field apply, you cannot shift it, because magnetic field, you cannot go more than 3 Tesla, because when superconductor is basically dead. Right? So already from this, from theory, you can say, okay, you have, if you don't have some control or control growth precision, which no one has, maybe 1 out of 100 nanowires could potentially work out, right? And then afterwards, you need to do, let's say, okay, you imagine you're there, but when you need to align chemical potential uniformly through the entire nanowire, but you have also fluctuations of chemical potential, right? Because you have a disorder, your gap is relatively small. So what is the probability that you would not just isolate or break your nanowire into pieces? So this could be also estimated. And then I think this is also like, let's say, why we started a little bit to look at the Microsoft, because the first paper, when it was published, they said that they had statistical analysis. I mean, they are Microsoft, they have computational facilities to simulate. And they stated in the paper that they have never seen false positive. So my students, they said, we're not caring much how probable it is that there's no false positive, but it's not possible that you have no false positive. Because for this, we can easily construct the model, and then we can see, okay, like we theorists, we understand how to get false positive, what to put in, and then we get immediately false positive. So we had a lot of discussions with Microsoft, are false positive possible or not? So we have demonstrated that there's quite a set of parameters that you can get false positives. It's just that when you do simulations around with disorder and simple model, we can say where these false positives are coming from. We have understanding. But when you have like a lot of disorder, everything, you have no understanding where your false positive is coming. But actually from our understanding in our models, they occurred quite often. We did not do systematic analysis, but I think the problem is also that we have, let's say, discussion in our community, how to treat disorder, are we allowed to make disorder average, right? Because it's a lot of discussion, let's say, if you're, yeah, because in principle, you can say the system is very short, and what you know in mesoscopic, that you can just assume that you have self-average, and here when you have approximately maybe 5-10 impurities, it's a question how much you should self-average. Because let's say, if you assume that you set impurities, maybe you get false positive in 10% of cases. But now, let's say, if you average, if out of 10, you say, okay, there's no false positive, and there's a lot of games on this level. But by measurements, the system is not self-averaging. Should not, because it's still small. But this is very full questions. I mean, depends on the model. I mean, there's some techniques, let's say, how you can measure them. So there's, let's say, but the example which I have shown, right, with this squeeze state, which is kind of nice, because here, already in the ground state, you should have a finite amount of magnons. And in this case, we can control basically by parameters, and by coupling, we can also estimate, let's say, how many magnons we have. We can also have reserved, but yeah. Generally here you want, so either you can use one magnon, let's say in domain swarm, then you can use it for coupling, or let's say in this system you go that you already in ground state have a finite number of magnons when you don't need to excite. If you don't, or let's say if you have isotropic model, of course you can start to drive with magnetic field when you excite magnons above a ground state, because you also know how their dispersion look like.
You've not been using it properly, I think. Okay, perfect. Next time I know better. So there's a bus that's going to be waiting for us in 10 minutes.